Alright, ladies and gentlemen, this question is number 7 on in-class assignment 8.6, and this one's about Texas Hold 'em and just how many, calculating some probabilities of getting certain starting hands. And if you don't know Texas Hold 'em, well, it's okay. We're just really just looking at just randomly being dealt 2 cards out of a whole deck of 52. So you can have this apply to Texas Hold 'em poker or not. That's up to you. Alright, so let's go through some of these problems here. We're looking for the probability we get 2 jacks, or any pair, or any 2 clubs, or any 2 cards of the same suit, or at least 1 ace, or 1 face card, 1 not face card, or 2 face cards, and then lastly, kind of a conditional probability that your opponent has 2 aces when you have an ace and a king. So let's try from the get-go, and there's going to be multiple ways of solving these problems, and I'll try to go through all 3 of them mostly, but I won't do all 3 methods for each exact problem, but I'll definitely be hitting up all 3 methods. So just to start with here, remember we're being dealt 2 cards out of 52 cards. So how many cards are possible? How many different starting hands, are possible? Remember, we don't care about the order in Texas Hold 'em. That is, you can, if you're dealt 2 cards, it doesn't matter if you were dealt an ace first and a king first, because you could shuffle them in your hand, so the order is not important. So that's going to make this a combination. In fact, we're just choosing 2 out of the 52. So there's 52, choose 2 possible starting hands in Texas Hold 'em. So that's 1,326 possible starting hands. Remember, put that in your calculator, 52 NCR2, and it should get you 1326. Now that was using a combination. If you like the permutation, okay, you could think there's 52 cards in the deck, so your first card could have been any one of the 52 cards. And then now for your second card, there's 51 cards left in the deck, so it could be any of 51 cards. But again, since you don't care about the order that they're dealt in, you got to divide that, in this case, by 2 factorial, since you're getting 2 cards and there's 2 factorial different ways of arranging those 2 cards. If you do it this way, you still get, guess what, 1326. And my cat is still just like playing with my pens, playing with my paper. I fed you twice. You're annoying me right now, kitty. Alright, so what's the probability you get 2 jacks? So remember, there's 4 jacks in the deck total, and you're looking to get 2 of them. So I'll solve this one both ways. So if you do a combination, and when you get used to combinations, I think you're actually going to find this is the easiest way to do this, because we're trying to choose 4 jacks. Sorry, we're trying to choose 2 out of 4 jacks out of 2 out of 52 total cards. So what that means on the denominator, how many ways could we choose 2 jacks? Well, there were 4 jacks, and we're choosing 2 of them. Out of how many possible hands are there again? Well, there's 52 cards. We're choosing 2 of them. So we're going to get here this 13 over 26, which when you put it in your calculator is this. Just a little, what I like to do, just to kind of make this a little more realistic, because a lot of times, especially with these small probabilities, you look at them and you're like, it's so small, I don't know if I could wrap my head around that number. Well, once this number is in my calculator, if I hit the inverse button, again, the inverse button is on the left row. It's that little -1. If I just hit that, right, as long as I have this number next, if I hit that inverse button, it's going to inverse answer this, and it's going to give me 221. What that really means is I've just kind of reduced this this whole number to 1 out of 100 1 out of 221. In other words, if I'm playing this game, I would expect to get 2 jacks about 1 out of every 221 times. Okay, that was solving it using combinations. If you didn't like that, you could use permutations too. Why not? Permutations. So in green here, I'll do the permutation. Now in a permutation, when I solve these, now I'm going to care about the order that they're dealt in. So in other words, the denominator in this case is always going to be 52 times 51 because I'm distinguishing between the order. Well, there were so how many ways could I get a jack at first? Well, there's 4 jacks, so I have 4 possible ways. Now, given I just got a jack, how many jacks are left in the deck? How many ways could I get a jack the second time? For instance, maybe the first card I got was a jack of clubs. Well, there's still a jack of spades, diamonds, and hearts, so there's still 3 jacks left over. And again, you put this number in your calculator. It ends up also being exactly that same number that we got before. Yay! Or 1 out of 100. Sorry, 1 out of 221 times. Okay, then is that the only way we can do it? Nope. Last way we could do this is with tree diagrams. Tree diagrams, I think in this case are useful. If you went through the super lotto problem with me, I don't think that the tree diagrams were quite as useful in a super lotto problem, but maybe you were able to do it and make it work. Alright, so when you look at the tree diagram, for instance, we could go, okay, what's the probability I get a jack, and then not a jack, but I'll be quite frank, I don't care about not getting a jack, because I only care about getting a jack. So I'm even just going to leave this part of the tree unanswered, because quite frankly, as I said, I'm only interested in the probability of getting 2 jacks. So how many jacks were there the first time around? 4 out of all 52 possible cards. Now, given that I got a jack the first time, what's the probability I get a jack the second time? Well, how many jacks are left in the deck? 3, correct. Out of how many cards are left in the deck now? 51. So my probability here of getting 2 jacks is going to be, just multiply these 2 guys together, and look at that. That's the same calculation I did up here, and that's going to end up being our 0.0045, which again is another smiley face, which again leads us to the answer. 3 ways of doing the same problem. I'm sure there's even more if you really wanted to. Same answer. Yippee. So what about any pair? Now this might seem a little trickier, but let's try doing this with combinations. I'll do this one with combinations and a tree diagram. I'm not sure if a tree diagram is going to work out that well either, but let's see here. Okay, so with a pair, we got, let's see here. I think the easiest way to do this is to really just use the result from our last problem. That is, we know there's a 0.0045 chance of getting a jack, 2 jacks. And when we did this in class, there was also the same probability of getting 2 aces. There was a 0.0045 chance of getting 2 aces. In fact, for any pair, there's a 0.0045 chance of getting any singular pair, that is, 2 threes. The probability of getting 2 threes is 0.0025. Probability of getting 2 fours is 0.0025. So I'm not even going to bother with the combination here. I'm just going to take my result from before and go, well, the probability I get 1 pair is 0.0045, and there's 13 different pairs I can get. So I could just multiply this now here by 13. 13 times 0.0045, and I get about a 0.0585, or a 5.85% chance I will actually be dealt 1 pair. I think that's probably going to be the easiest way of doing it. Is there another way of doing it? Oh yeah, you betcha. Let's try a tree diagram then. So here's how I would look at this. So we're going to get, if you think about this, so it doesn't even matter what the first card is. So the first card you're dealt with is, I don't know, any card. And your probability of getting any card is it's certain, right? If you're dealt a card, the probability of getting any card is 1. But now, once you're given that, once you got that card, what's your probability now of getting that same exact card? Well, it's going to be same card. The probability, there's whatever card that was. Say it was a jack. Now there's 3 out of 51 jacks left. Or if it was a heart, I'm sorry, not a heart. If it was an ace, there's still a 3 out of 51% chance. And so really what this probability is going to be is just 3 out of 51. And if you multiply, I'm sorry, if you put that in the calculator, it's that. Why the discrepancy? Well, it's because I rounded this number when I multiplied this by 13. So that's the probability of getting any card. And just kind of revisiting this combination part, how I started this, if you think about this, it could be any of the 13 suits, and I'm choosing 4 out of 2 of any of the 13 different cards over 52. Choose 2, and you would have gotten your same answer. I think actually more exact if you put that in the calculator this way, because again we rounded that 0.0045. Alright, that wasn't too bad. It was horrible. Okay, 2 clubs. You try this one. Try combination or tree diagram. I think either one is going to get you to the answer here. Pause it. Try it. Hey, you paused it. Thank you. Thanks for pausing and trying it. What'd you get? Well, let's see if I get the same thing. So here's how I'm going to do this with a combination. So again, there's 13 clubs, and I'm trying to choose 2 of them. So I just care about any 2 clubs out of all possible decks. I'm sorry, out of all possible hands. And I get 78 possible ways of getting 2 clubs. Wow, this number looks familiar. 0.0588. Huh. Whoever thought there'd be the same possibility of getting a pair? Well, yeah, so there you go. That's kind of cool. I actually didn't realize that when I was doing this, but see if you can justify to yourself why the probability of getting any 2 clubs in particular is the same as getting any pair, excuse me. Okay, how about a tree diagram? I could either get a club or not a club. And again, there's 13 clubs out of the deck, and I don't care about not getting a club, so I know from the beginning there's a 1 out of 4, 13 out of 52 chance of getting a club. Now what about getting that second club? Again, I'm not going to worry about not getting a club because I'm not interested in not getting a club. Well, there's 12 clubs left in the deck if you got one the first time, and there's 51 cards left in the deck. So here the probability of getting a club is going to be 12 times 13 over 52 times 51. And if I put that in my calculator, I get, I hope it's the same, yay, it's the same. The same as I got above. Smiley face. So how about any 2 cards of the same suit? Now again, I can use my result from before and just go, well, the probability that I got a club, 2 clubs, was 0.0588. Now that could have been 2 clubs or 2 hearts or 2 diamonds or 2 spades, and since all those are mutually exclusive, I could add all 4 together or just take my result from before and multiply my result from before. So got that answer fresh on my calculator. I got 0.2353, about 23.53% chance of getting 2 cards of the same suit. So that's one way of doing it. And again, how did I do that using the combinations? I really said, well, there's 4 suits, and I'm trying to, out of those 4 suits, each have 13 cards. I'm trying to choose 2 of those 13 cards out of my total possible starting hands, and I would have gotten the same thing there. Tree diagram. Can you do this with a tree diagram? Oh yeah. For instance, the probability of getting, so we're just looking for any two suits. Again, the first card could be, you could get any card, whatever card that is. There's a 1% chance of getting any card, right? I'm sorry, not a 1%. The probability is 1, or there's a 100% chance. But now to have that card the same suit, well, how many cards? How many of the same suits were out there? Well, there's whatever suit that was. There's only going to be 12 left out of 51 total. And guess what? 12 divided by 51 is, yeah, you guessed it right, 23.53%. So again, whichever method floats your boat. Okay, what's the probability you get at least one ace? Alright, so this one ends up, I would say a tree diagram is going to be the easiest way to do this one, but let's see how to do this with a combination. So at least one ace. Alright, so we can have, for instance, so at least one ace, that also includes the possibility of getting two aces. So, so we could either have like an ace and something else, or we could have an ace and an ace. Let's see if we care about something else or not. I think we do. Alright, so how many ways would there be to have, let's say, an ace and something else? Well, so my first card, again, I don't care about the order here because I'm going to use combinations. I'm trying to choose one of those four aces for my first card. But now my second card, for this not to be an ace, I want to choose, for instance, how many cards are not an ace? There's 48 cards that are not an ace. And I can choose any one of those 48 cards that are not an ace. And that's going to be divided by the total 52 cards. So this would be the probability that I get exactly one ace and one not ace. Why again? Because this number here, 4 choose 1, that would represent how many ways I could get one ace. And this 48 choose 1 is going to represent how many ways I don't get an ace. Now I am going to have to add the probability that I already found before, the way my probability of getting two aces, because that's a possibility. And the way I had set this up is this here would always represent not being an ace. So I do have to consider the fact that I did get two aces. And I've done that before. That was 4 choose 2 divided by 52 choose 2. So if I do this, this should be 4 times 48 on the 4 times 48 on the numerator. I get 192 over 1326 plus, in this case there was 6 out of 1326 ways of getting exactly one ace. I get 198 over 1326, which is 0.1, almost 15%, 0.493. And I'm just going to inverse this for fun. I get about 6.7. That actually means about 1 out of 6.7. That means 1 out of every about 6.5, 6.7 times, about 1 out of 7 times, I'm actually going to get an ace. You probably wanted to do a tree diagram instead, right? I don't blame you if you wanted to do a tree diagram instead. That would have been easier on this problem. So let's try a tree diagram. We could either get an ace or not an ace for my first card, and my second card I could either get an ace or not an ace, and I could get an ace or not an ace. And let's fill stuff in here. My probability of getting an ace is 4 out of 52. Then my probability of not getting an ace would be 48 out of 52. So if I got an ace the first time, the probability I get an ace the second time, well, there's 3 aces left out of 51 total. Or else here I could have got an ace the first time and gone, that's 48 cards that aren't an ace if I got an ace the first time out of 51 total cards. Or if I go to the branch underneath, I didn't get an ace at first, so the probability I get an ace again, there's still 4 aces left in the deck out of, sorry, that's supposed to be 51. And the probability I don't get an ace, given that I didn't get an ace the first time, well, there's now 47 cards that aren't aces left in the deck if I took one card that wasn't an ace out, and there's 52. Alright, so there's a couple ways of doing this. I'm going to actually end up using the complement rule because it's going to save me, it's going to actually save me a little bit of work. So the probability I get at least one ace is going to be 1 minus the probability. I'm going to use the complement rule here. Again, this isn't the only way I do it, but it's going to be 1 minus the probability I don't get any aces. And the probability I don't get any aces, that's going to be the bottom branch of my tree. So that's going to be 48 times 47 over 52 times 51. Boy, I hope I get the same answer I got before. It would be awkward if I didn't, right? If I multiply this branch, I get 85.07 if I round it correctly. So my probability that I get at least one ace should be 1 minus that, and once I do that, I get 14.93. Oh, isn't that what I got up here? Yay! Both would have worked. I could have also calculated each one of these and added them together. Why did I use the complement rule? Because I recognized that, hey, again, the probability to have at least one ace would be 1 minus the probability I don't have any aces, and that way I only have to multiply this branch once and then just subtract it from there. Remember, if I had all these numbers, they would all add up to 1. So I'm just going to be lazy, use the complement rule. Why not? Man, can you believe I'm still talking? Gee. Alright, what about one face card and one not face card? Alright, so with the face card, that could be a jack, king, queen of 4 suits. So there's actually 4 times 3, there's 12 different face cards out there. Because 4 suits, 3 different face cards. So, let's just tree diagram this. Just so I could either get a face card or not a face card. And again, here I could get a face card or not a face card. And here I could have gotten a face card and not a face card. So I'm looking specifically for a face card and one not. And again, this could be in any order with the tree diagram. Since the tree diagram, we do care about order on the tree diagram. So that means I'm going to have to do these two and multiply them. Okay, so how many face cards were there to begin with? Well, there's 4 out of 52, which means that there's, let's try that again, it wasn't 4 out of 52, it was 12 out of 52, thank you. Which means that there's going to be 40 out of 52 not face cards. Now, had I gotten a face card the first time, there's 11 out of 51 face cards out there remaining. Had I gotten a face card the first time, there's 40 out of 51 not face cards remaining. Next branch, so I didn't get a face card the first time, so there's still 12 out of 51 cards left. And I don't think I'm going to need the bottom branch. I'm not even going to bother because I don't care about not getting 2 face cards. In fact, I only care about getting 1 face card and 1 not, so I'm going to multiply these 2 together. And if you actually look, that's going to be 12 out of 52 times 40 over 51. The other way is going to be 40 over 52 times 12 over 51. They're going to, since multiplication's commutative, they're going to equal the same thing. In other words, I could just calculate it twice and double it, and I'll get my answer. 12 times 40 divided by 52 times 51. I get 0.1810 when it rounds to, so I got to double that. So the probability that I get at least 1 face card, or that's not 1 face card, that's exactly 1 face card and 1 not face card. I'm not going to write it out here again, but it's 2 times 0.81 or 0.362 or a 36.2% chance I get exactly 1 face card and exactly 1 not face card. It's still going here. Okay, two face cards. Okay, so two face cards. I could totally use that tree diagram I got right there. In fact, all I have to do is multiply that top branch and I'm done. So you could do it that way, or let's try another way here. Let's try combinations. I'm only saying that, let's try this, to show you a different method of solving it. You could still use that tree diagram to begin with, but let's try a combination. So again, we know there's 52, choose two possible cards. Well, I'm trying to choose two face cards. How many face cards were there? There was 12, so I'm trying to choose any 12 of those two face cards in any order. So it's going to be a combination. And if I do 12 NCR 2, I get 66 divided by, we did that already, so 66 divided by 1326, I get 0.0497. I'm sorry, 8. That's going to round up to an 8. So 4.9, almost a 5% chance that if I'm dealt two random cards, they're going to be both face cards. And again, I'm going to verify, I went back to the tree diagram here, that it should be that top branch of that tree, so 12 times 11 divided by 52 times 51, and oh, it's the same number, 0.0498. Alright, last one. Your opponent has ace-ace, given that you have ace-king. This happens a lot in poker. You know your own cards. You don't know anybody else's cards, so you want to kind of go, well, hey, my opponent's kind of betting strong. He's like, hey, it's like I have two aces. Well, I have ace-king. That's a good hand. What's the probability, if I have ace-king, that my opponent has pocket aces? Because if he does, I got to run away. I'm going to lose, most likely. Alright, so I'm going to use a tree diagram here. Or a combination. Let's start with a tree diagram and then I'll do a combo and then we'll call it a day. Sound good? Sound awful? Oh man, I can't believe I'm still talking. 30 minutes. It's Sunday morning. Should be out having fun. Okay, so this is not going to be me now for the tree diagram I'm building. I know what I have. I am looking at my opponent. So this tree diagram is not going to represent my probability, but my opponent. I know what I have. I have ace-king. So I have two cards out of the 50 in the deck. How many cards are left in the deck that I don't know what they are? Good, 50. How many aces are left in the deck? Because I have one of them. There's 4 total. So there's 3 aces left in the deck. So the probability my opponent has one of those aces is going to be 3, because there's 3 aces left out of 50 cards in the deck left, because I have ace-king. Okay, again, I don't care about the rest of the tree at this point. I only care about that top branch. Because if he's got his first card's an ace, what's the probability his second card is an ace? Well, how many aces are left in the deck? 2. How many cards are left in the deck? 49. So it's going to be 3 out of 50 times 2 over 49. So that's 6 over 2,450. Don't ask me. Wait. Yeah. Don't ask me why I know that. Okay. Now I'm second guessing myself. Yeah, I should be second guessing myself, right? 24 times, no, 50 times 45, 49. That's a 49, I swear. Yeah, I was right. I didn't need to second guess myself. That's a 49. Okay. So 6 divided by that is 0.0024. So good news, if you have ace-king, there's about a 0.25% chance your opponent would have ace-ace, or about a 1 in 408 chance. 1 out of 408 times, if I have ace-king, would I expect my opponent to have 2 aces. Well, that's good news if you're playing poker. Okay, I think that's it, right? You want more? Neither do I. Alright, I hope that all helps. Happy studying, and have a good day. Bye-bye.